Discrete, section 6.5. It's called Probability Part 2. In this section, we're going to deal with a big problem that's called the binomial probability distribution. This is a situation where you've got two things that can happen, and really only a finite number of ways. It's either true or false, it's male or female, it's, white or black, on or off, things like that, where you can have two things. That's one of the reasons they call it binomial. It has a fixed number of trials, and it can use our NCR, the combinations, to help us count ways, at least, of doing things. Remember, that was n factorial over n minus r factorial. But then it's got this r factorial out here also in the denominator. You can find that in your calculator under the math prob, and we'll use that. So let's suppose we're playing a game. This guy named Chuck came up with it. You toss a pair of die one at a time. The dice. One at a time. If you get 2 5s, then you get $5. If you get 1 5, you get $1. And if you get 0 5s, you have to pay $1. That's his game. And see what something called the expected value. If you would play this game many times, how much would you expect to win or perhaps lose in this game? Well, one of the best ways to look at this is really with a tree. And you have 2 dice that you're rolling, and you either get a 5 or not. And then a 5 or not. This situation, you could get a 5 or not. So, if you get a 5 on the first throw, then you know you at least get $1 back, get your dollar back. If you get a 5 on the second throw, then you get the $5. But if you don't, at least you get your $1 back. Even if you don't get it the first time, you might get it the second time and get your $1 back. It's this not that is the two, the one where you lose the $1. So, how much are we going to play for this thing? I guess, how many ways, if you roll 1 die, is there to get a 5? Well, there's only 1 5 out of the 6. And for not, you get 5 out of 6 ways of doing that. I wonder if you can even read that. Let's do that a little darker. So 1 out of 6 and 5 out of 6. Because these are independent events, the second die, it doesn't matter what you got the first time. It won't affect the second throw. So you still have a 1 out of 6 and a 5 out of 6 for both of these. And remember, on a tree, you multiply as you go out. So 1/6 times 1/6 is 1/36. A 1/6 times 5/6 is 5/36. A 5/6 times 1/6 is also 5/36. And 5/6 times 5/6 is 25/36. Okay. Now, what's sort of interesting, you notice there's 2 of these situations. So you really get 10 out of 36. Now, you might say, gosh, if I have to do this for a tree, just 2 dice are going to be a little bit of a tree. 3 dice, you'd get another one, and this thing keeps doubling each time. Am I going to have to do that each time? No. you can use the NCR. If you have 2 dice and you want to get 2 5s, that's what you call your, I guess, your winnings. Then if you put that in, you'll get a 1. There's one way to do that. If you have 2 dice, taken one at a time, 2 5s for these 2 dice, and you get 1 out of it, you get a 2. This is the 2 ways of doing that. And 2 dice, and you get none, it is also 1, which is the one way here. So this is how many ways of getting a 1 out of 36, how many ways of giving a 5 out of 36, how many ways of getting a 25 out of 36. So in that way, you could have said there are, if you want to think of it this way, to get, this is the number of ways, you'd need the probability for that. You just need the 1 times 1/6 times 1/6, and you can sort of set these up. There's 1, if you do this 1/6 1/6 for each throw. This is more like the fundamental rule of counting. If there's 1 out of 6 ways to get the first thing and 1 out of 6 ways to get the second thing, sort of like that. And 2 times, well, you might get a 1 out of 1/6, get 1, but you miss 1. And then there's one way to get the 5/6 on the first throw, 5/6 on the second throw. And it gives you the same setup here. So you can do this several different ways. Now, what we need to do, though, is really set up what they call as an expectation. How much are you going to win or maybe lose, so you don't want to play if you're doing this stuff. And you set up a table. So the table will have the amount that you might win. Let's see, we got $5 for that first way. We got $1 for the second way, and a negative $1 for the third way. That's where you're going to run into problems. Then you've got the probability. This is the 2C2 1/6, 5/6. See, 1/6 is squared because there's 2 ways of doing that. And 5/6, there's no ways that you'll get that. So you can use these powers also. And it then uses this same pattern. Number of ways, 2C1, 1/6 is 1, and 5/6 is 1. And then you have a 2C0, where 1/6 is 0 and 5/6 is 2. And the same idea, same thing going on here. Instead of doing 5/6 times 5/6. So you can set the 2 different ways up, and you get then the product of these 2, the x times p of x. Because we know that this is, when you multiply this out, you get 0.028 times the 5. You get 0.1389. This, if you multiply this out, you get 0.278 times 1, so it's 0.2780. I'm sorry, 2778. If you take it 4 places, 2778. And this one, 4 places, negative 0.6944. You add all these together, these don't outdo this thing because this is 0.69. You get a negative 0.2778. Or you can expect to lose 28 cents. So this game really favors good old Chucky, who's trying to get some of your money. Now you might say, gosh, that's great. When am I going to use this next? Well, let's go to something that may not be as this is nice to think about. The Challenger situation, when they had the space shuttle explode with the teacher on it, that'll be the next part of this. Now this is going to be a really simple view of that, I guess, tragedy. Suppose P is the probability that an O-ring does not fail. And they had that figured at 0.977. So the opposite of P, or Q, is the probability that the O-ring does fail. So it's 1 minus this, which is 0.023 that it fails. Okay. Suppose each booster has 3 O-rings. And there are 2 boosters for each launch, which gives us 6 O-rings. O-ring is really just what it is, like a rubber gasket in the shape of an O. So we're going to look at the X, the number of O-rings that fail. Okay, and then there'll be the P of X, the probability that it will fail. And then we'll look at the product, X times P of X. And when we add all those up, that'll be the expected value, or the expected probability that one would fail. And perhaps they looked at this the same way, I don't know. This is probably very simple compared to what they would look at, but it's sort of an interesting look. So we could have none fail, 1, 2, 3, 5, or all 6 fail. The probability that none fail. Remember what we're doing the last time. This was the 6 choose 0 with 0.977. If none fail, then this will be to the 6th power and the 0.023 to the 0 power. And of course, this is an easy multiplication because it's times 0. So this thing really comes out to be 0 here. Now we've got this 1 times, this is 6 choose 1. Now the 0.977 will be with 5, and the 0.023 with 1. And what you'll get for that then is 0.12284. You can keep that pattern going. This will be 6 choose 2, the 0.977 to the 4, the 0.023 to the 2, and you keep using that pattern all the way down here. You get the following numbers: 0.1446, 0.00068, 0.4 zeros, and 1 6, 0. See, 1, 2, 3, 4, 6 zeros, and a 1 9, and 0. How many zeros? 1, 2, 3, 4, 9 zeros, and a 1. I'm sorry, and a 9. And then you add those all together. Now you might say, oh my gosh, this is horrible. I'm going to be all confused and everything. Well, hopefully you can see your calculator, and we're going to do this on the calculator. Let me see if I can zoom in on this.